Okay, so in this session, we will introduce CFD basics and the use of ANSYS Fluent in engineering application. You already have taken fluid dynamics as a core course in mechanical engineering, and you know that fluid dynamics is an interesting and challenging field for study and research. And in real world, almost everywhere fluid is present. So we need fluid dynamics to describe or model any flow. Now, in CFD, fluid dynamics is very important. Already CFD is computational fluid dynamics. And we are, if you want, solving fluid problems, but using numerical technique, not using analytical techniques. Okay? So now, in any fluid that we have three basic physical laws that we use in general. First, the continuity equation, which is which represents, if you want, the conservation of mass, the momentum equation, and you know that a widely known specific case where we consider Newtonian fluids with constant viscosity and constant density. We name these momentum equations the Navier-Stokes equations, and they represent Newton's second law applied on the fluid. And the third relation is energy equation, which represents the energy conservation and takes into account also all possible losses that can take place due to turbulence, due to heat loss, etc. Now, you remember that we can write conservation equations in differential form. So in CFD, what will happen is that we will use these relations, but we will write them in a numerical way. So we will try to not have, if you want, derivative terms. We'll transform derivative terms to numerical terms. What do we mean by this? For example, let us say you have in an equation, for example, dx by dt, for example. Instead of treating it as the derivative of x with respect to time, which requires knowing x and deriving it as a function, we can write it as delta x over delta t, where delta x, let's say, is x2 minus x1 over t2 minus t1. And then if you decrease delta t, okay, the more you decrease delta t, then you will be closer to the real derivative, okay? So we will see then by doing this transformation, we can transform a differential equation form to an algebraic form that can be solved using numerical schemes. So if you remember, the conservation of mass applied for an infinitesimal control volume consists of the following. You have the accumulation term. This is a transient term, which represents the accumulation of mass in the control volume, plus sum of m dot out, which represent fluxes of mass getting out from your control volume, and minus sum of m dot n, representing the fluxes of mass entering the control volume. So this relation, okay, can be transformed to an algebraic relation and solved numerically for the continuity equation. Now, similarly, you can apply, if you apply it now in detail and you want to derive the differential form for mass conservation, you should consider all fluxes as we talked about, all fluxes coming in, all fluxes getting out, and the transient term. So if we want to detail this relation, we should express the mass flow rates at inlets and outlets. So I will not go over, if you want, details, because already you know this from fluid mechanics, okay? But at the end, when you develop this relation, you can find, you can end up with the continuity equation. So after simplification, you get your continuity equation. Now, also, when you apply Newton's second law in X, Y, and Z on your fluid element, in case we are dealing with constant viscosity and constant density, you obtain the Navier-Stokes relations. And these relations, you will derive them again in the course with in the course material. Okay, so here you have, just to remind you, the first term represents the local acceleration, which is the variation of velocity, the partial variation of velocity with respect to time. And you have also acceleration with space. So these terms represent the convective acceleration. And you have equal to these accelerations, the total acceleration, if you want, is due to the different forces acting on your system. So you can identify gravitational force per unit mass, pressure gradient force per unit mass, and viscous forces per unit mass. Okay, so these are the famous Navier-Stokes relations, and as you can see, they are complex, and it was been a very challenging process to solve them analytically. Researchers have tried a lot to come up with analytical solution, and you had a big prize for the scientists who can solve it, but no one were able to find an analytical solution. So this is, of course, for some simple cases, they have analytical solution. For example, if you have laminar flow in a circular duct, quasi flow, you can find a solution. Flow between parallel plates, you can find a solution, and you have developed this simple solution in fluid mechanics. Now, when you go to turbulent flow, and this will affect a lot, and this will add complexity to your relations, and it will be more challenging to solve them. And also, when the geometry is complex, you don't have simple geometry, also this complicates the analysis. This is why numerical techniques and experimental methods are used to find solutions for these relations. So as we said, Navier-Stokes equations were a big challenge in research. They are nonlinear partial differential equation, and there is no general closed form solution. And as I told you, it was one of the 7 Millennium mathematical challenges, which holds a prize of $1 million. Okay, closed form solutions exist for special simplified problems as flow in circular ducts, laminar flows, of course, uh, flow between parallel plates, flow in annulus. So all of these simple cases were analytically solved, but for more complex competitions, for more complex problems, as we'll see now in next slides, computational fluid dynamics techniques are used, and also experiments are used, but CFD is more used because, you know, the complexity of experimentation and the cost it requires. So in general, what we do, we perform just some experiment to validate that our CFD model is working. And once the CFD model is validated, we conduct a parametric study using CFD. Okay. Now, in order to solve these equations, we need to supply the geometry, of course. And in CFD, the first step will be to draw your geometry. Then you will divide your domain into small control volumes. So this is the meshing process. We divide it into small parts. Then you will write the boundary conditions for the solution of your domain. You should know what are the inputs needed. And for example, if you want to study the flow over a sphere in a wind tunnel, for example. You need to provide the upstream velocity. You need to, so this is a boundary condition. Okay. If you have a transient problem, you should also write the initial conditions at t equals 0. What what was the velocity? What was the temperature? And then when you solve, you will have variation with time of all of these variables. Now, uh, we can try to simplify the equations as much as possible by noting the flow geometry and other informations. So sometimes you have terms that are negligible, so this will lead to some simplifications. If you want, if you want to solve analytically, if this is possible, okay? And you will integrate the equation with respect to the different variables, and then apply the initial and boundary conditions to get the constants of integration. Now, what are problems that require CFD? As we said, in cases we have complex geometry. For example, if you want to test the design of a car, you want to find drag and lift forces on a car, on a BMW car. You want to improve its design. Of course, you cannot do it analytically. Okay, you need to do or experiments or computational fluid dynamics analysis. So here you can just draw the geometry of your car, set the condition of the coming flow, and you can study by using computation fluid dynamics, you can obtain the profile of velocity, the profile of temperature, the profile of pressure around your car. This will allow you to know the constraints acting on your car, the maximum pressure is at which location. Uh, let's say if you are interested into reducing drag force, what is the design, what is the curvature that can reduce drag, etc. So computation fluid dynamics will permit to you to calculate drag forces, lift forces, and find the coefficients that are of interest for you. Now, as we already said, we have several ways to solve a problem. Okay, so the first method is the analytical or theoretical approach, using laws and theories and associated equations such as Newton laws of viscosity to solve a fluid flow problem. And this solution will be exact. Okay, but the problem is that these analytical solutions are limited to simplified problems and cannot be extended to all fluid engineering problems that we have. And the majority of engineering problems that we face in real life doesn't have an analytical solution. This is why we have two other main approaches, as we said, the experimental and the numerical one. The experimental approach consists of doing experiments and try to understand the phenomena and relation between the different variables affecting the problem, such as wind tunnel experiments, which help to design and optimize the external shape of airplanes, ships, and cars. So in aerodynamics, experiments in wind tunnels are widely used. Okay, but you know that uh, experiments take time and have a high cost. This is why to not have to do everything experimentally, we can also develop a numerical approach that will solve the fluid problem using numerical techniques. And of course, these solutions are approximate and not exact, but in order to test if they are close to reality or not, we can validate the model. So we can do a small experiment to validate the CFD model. This will allow us to tune the parameters. So in case, for example, the mesh should be enhanced in order to have better results. If we have a transient application, we might have to decrease the time step to reach more exact solution, etc. So experiments can allow us to tune our model, and once our model is working well, we can use it to perform a parametric study. So since we talked about numerical techniques, mainly this is computational fluid dynamics. So CFD is computational fluid dynamics, It consists on a set of numerical methods applied to obtain approximate solutions of problems of fluid dynamics and heat transfer. So CFD is not a science by itself. It's a way to apply the methods of one discipline, which is the numerical analysis, to another science, which is fluid or mass transfer and heat transfer. Okay. Now, why we use CFD? So already we have said that CFD solutions are not exact. So why not to use the analytical approach? We already mentioned that the analytical approach does not always have, it doesn't we do not have a solution for all problems we encounter. This will force us to go to other techniques, numerical or experimental. It's true that experimental approach might be more reliable because we can do live experiments and measure values, such as wind tunnel experiments. But why we don't use it instead of CFD? CFD is used because there are many engineering problems that can be solved analytically, and the experimental approach is difficult to use and it needs time and cost a lot. This is why CFD is the most common technique used to solve complex engineering problems. So as we said, for the theoretical approach, it gives exact solution, which is a great advantage, but the analytical solution is limited to a number of problems, usually formulated in an artificial and idealized way. On the other hand, the experimental approach is reliable and depicts real-world situation. For example, if you want to perform in aerospace industries some experiments on models of airplanes or cars, you can use wind tunnel experiments, but sometimes these are very expensive and can present technical difficulties. So it might take several years before an experiment is set up and all technical problems are resolved, especially if we are talking about uh, airplanes, cars, etc. And that you know, of course, from fluid mechanics that you can construct a prototype and you don't have to work on the largest scale. You can construct a model that has similar conditions to the prototype. When we talk about similarity, then we have same pi groups, if you remember. Okay, but even that we can extrapolate these results. At the final stage, when we should test the real prototype. So when it comes to designing a car or airplane, at the end we do some tests on the final design, and this requires a lot of time. Okay, so CFD can help us to reduce this time by conducting parametric studies through CFD. Now we will go over some very important applications of CFD. CFD is a very powerful technique and spans a wide range of industrial and non-industrial applications. So already we talked about aerodynamics of aircrafts, of cars, etc. So you can compute drag and lift acting on them. You can study also, for example, combustion in internal combustion engines. So you can study the combustion process. You can study what is happening in gas turbines. You can study biomedical engineering applications as blood flow through arteries and veins. You have a lot of application also in environmental engineering. You can study distribution of pollutants in space. So as you can see, CFD has a variety of applications. This is why it's a very interesting field. Let us see now some figures showing these applications. We already talked about aerodynamics, so you can study the flow over a car, over an airplane. Also, as you can see here, you can try to see how to design your spoiler or how to have the curvature of your car in order to reduce drag on your car. And here we can see, for example, when you are designing an airplane, also you can study velocity and pressure field around it. Here, for example, we have flow over an airfoil. Okay. Concerning colors, we will learn together how to read these maps. Okay. So here, for example, you have combustion. This is a thermal engine. You can see what is happening inside the cylinders. These are the valves, etc. So here, for example, you can have representation of the temperature. Okay, how the temperature is varying, and at the same time you can present velocity curves to see how flow is entering and exiting the room. You can see here a pump. Okay, you can study what is happening in a pump. You have, for example, also you can study, for example, here flow over a sphere in a wind tunnel. Like here, for example, if we do some analysis, okay, this is the representation of the velocity field over a sphere. Okay, for the colors, always red is the highest values. Red colors represent highest values. And of course, for each figure, you should have a legend with it. So you will have a legend showing you the map of colors and giving you units, of course. Okay. So here you can see, if you do in some interpretation here, you have nearly a uniform flow coming towards the sphere. Now, what will happen as you approach the sphere? If you remember, if you do Bernoulli analysis, so as you are approaching the sphere, what is happening is the pressure will increase and the velocity will be reduced, and this is the stagnation point where you have zero velocity, and you have separation of airflow. So you have, this is the stagnation streamline. You have separation of flow from the two sides of the sphere. This is why here you have a region of very high velocities, because from continuity equation, the mass flow rate is conserved. So the area here is reduced a lot, which lead to high velocity in this region. While here you have the wake region, formation of wake region due to separation. So here the velocity is nearly very close to zero. And then you have separation of the flow, as you can see here. So this is a representation of the velocity field over a sphere. Here, for example, you can see the velocity profile in a circular dot. Okay, so here, for example, you can verify the analytical solution obtained from for a laminar flow. If you have a laminar flow, you can verify the profile of velocities that we learned, the quasi-flow profile, where you have zero velocities at the wall due to the non-slip condition and a maximum velocity at the center. So you can illustrate this by CFD also. Another application is heat transfer. In this figure, we can observe, for example, the cooling or heating of a fluid in a heat exchanger. So as you can see, let's say you have a fluid, let's say, entering here, like you have a fluid moving in this direction and another one moving in this direction. Okay, and as you can see, this fluid, for example, is cooled as it moves through the heat exchanger. Okay, so this is a heat transfer application. And you know, you can study different types of heat exchangers, different forms. And in your we will do a project in this course. We will take one of the applications and study the temperature, velocity, pressure profiles, etc. Now, CFD can be performed by a simplified code. So you can develop your own code. You can write a MATLAB code, a C code to develop CFD techniques, numerical techniques. Of course, when it involves complex geometries, you need a software that is a package. For example, if you want to test a car, let's say, you want to develop a very powerful tool. So in general, we have softwares that implements all numerical techniques developed in the CFD. One of these powerful software is ANSYS Fluent. You have also OpenFOAM, COMSOL, etc. In this course, we will work with ANSYS Fluent. All softwares are quite similar. They all have same concepts. So if you know to work with one, you will not face difficulties in working with others. But of course, each software represents its own advantages. So we will work together with ANSYS Fluent. So please try to download ANSYS Fluent. You can download the free student version, okay? And also you can do it at the university in the labs. I can download it for you. So you can download any version you want. You are not restricted to a certain version, okay? The one that is available, you can download it.
But the recent versions are a little different from
Yes, it's true. It's true.
2013.
بس هن شوي في difference بس إنه كتير بيشبهوا بعض يعني ما حتلاقوا مشاكل. Don't worry about this. Okay. يعني أكيد they implement everything old plus they implement some new features. Okay.
اوكي يعني فينا ننزل تبع 2022 او 2021.
فيكم تنزلوا لبعضكم مش مشكلة. Okay. Okay. Now, problem solving using commercial CFD packages. CFD codes are structured around the numerical algorithms that can tackle fluid flow problems. In order to provide easy access to their solving power, all commercial CFD packages should include sophisticated user interfaces to input problem parameters and to examine the results. يعني إذا بدكم السوفت وير مثل بلاك بوكس يعني كله implemented بقلبه وأنا just I interact with it through an interface. I select the numerical models I want to use. I draw my geometry. I put the inputs and CFD will do its own computation. The software will do its own computation and give me the results. Okay, so we have three main steps in all CFD codes. The first one is the preprocessor. The preprocessor consists of creating the geometry. You will create it, of course, and meshing it. This means dividing it into small parts, into control volumes. Okay. The second phase is the solver. This part consists of the numerical solution of the fluid flow equations in the computational domain. And you will specify using the interface of the software what are the numerical methods you want to use. So we will learn numerical techniques. In the course, you will learn numerical techniques. And in the lab, we will apply them. For the post-processor, you have in this steps, result of simulation will be analyzed and represented in a useful form. So this is the final step. When your computations are done, you can take results. You can observe profiles of velocity, temperature, concentration, pressure, etc. In ANSYS Workbench, so the software you will download is ANSYS Fluent. ANSYS Fluent هو part of ANSYS Workbench. يعني إن إحنا بننزل ANSYS Workbench and then we select بقلبه ANSYS Fluent. Okay. You have the design modeler and meshing works as preprocessor. Fluent is the solver and CFD post is the post processor. هلا حنشوفهم شوي كinterface to be familiar with them. Okay, so you have different methods of numerical solutions in CFD. You can use the finite difference method, you can use the finite element method, and you can use spectral methods. In ANSYS Fluent, we will use the finite volume method. Okay, so the finite volume method is a special case of finite difference method. It's a very popular method, and it is the method that is the base of ANSYS flow. So ANSYS is an engineering simulation software, and it was developed a long time ago, and it was, if you want, enhanced with time, and until now we enhance it. Yani we implement continuously new codes, new algorithms for it. You can also, what is nice about it, you can also implement your own code with it, and you can write a C code and interact with ANSYS Fluent, let's say to create, for example, a boundaries that is varying with time, for example. So you can, this will allow you for changes, for continuous changes, because if you have an application that is not directly present in the package, coding will allow you to implement what you want. Okay, so this is a nice feature about it. And ANSYS Fluent is one of the most popular commercial CFD software packages, and we will use it in this course to solve engineering problems. So as we said, it is based on the finite volume method. So the domain is discretized into a finite number of control volumes, and the general conservation equations of mass, momentum, energy, and species are solved in a set of control volumes. Now, to solve the engineering problems using ANSYS, as we said, we have different steps. First, we should do a pre-analysis of the problem to understand. In the pre-analysis, for example, you can do some simplification. Let's say if you have enough space, you say, for example, I just need to represent the desk and the occupant and the computer. No need to represent, for example, let's say if I have chairs at corners, they will not affect a lot the fluid flow, so no need to put them. So you can do some simplification and eliminate objects that might not affect your problem significantly. This will allow you to simplify your geometry, and because more your geometry is simplified, more the results will be, if you want, easier to obtain, because a complex geometry will require a more complex mesh and will require more time to solve. So if we can do some simplifications without affecting the physics, we can do it in the pre-analysis step. Then we will draw the geometry. So we will draw in ANSYS. Of course, you can draw it also in AutoCAD or Inventor, and you can import it to ANSYS. But in general, I advise you to draw it in ANSYS because it will reduce some possible complications. And after drawing the geometry, as we said, we divided into small control volumes. This is the meshing step. After this, we do the physical setup. This means that we introduce boundary conditions. We say, for example, this is the velocity at the inlet. If you have a room, for example, is equal to this value. The temperature is equal to this value. So we should give inputs. And then we should specify, of course, what are the numerical techniques to use, what are the schemes that we want to use. And after this, we can start the calculation. So we have the numerical solution step. And at the end, we can get the results and verify and validate them. You can always check if the solution is physical or not to know if there is something wrong or missing, so we can fix it. So these are the main steps in solving a CFD problem. Now, ANSYS Workbench is a graphical user interface that allows the user to use all the required tools, software from a single place. You can access the preprocessor solver and post-processor tools from ANSYS Workbench, and you can control your workflow between variable tools through Workbench. So here, this is the interface that you will have. So the symbol of ANSYS Workbench is this one. Okay. Once you open ANSYS Workbench, you will have all of these options. We will work together with Fluid, Flow, Fluent. So you select Fluent. When you select Fluent, you will have this window will open, which is divided into the steps you need to go over. So first, you have the geometry, where you will create the geometry of your problem. Then you go to mesh to divide it into small control volumes. Then you go to setup in order to set the boundary conditions. Then, and of course, the numerical schemes that you will use for your solution. Then you go to solution, and here you will run the computation and wait until convergence is reached. And finally, you can explore your results. So these are all steps that are summarized in the interface. Okay. So hopefully next time you will start together to work with ANSYS and to see how to use these tools. So here we will detail a little bit the steps we talked already about. So as we said in the pre-analysis, you want to solve a real-world engineering problem numerically using ANSYS. So you will need boundary condition, you will observe the real physical situation, or you will obtain data so that you can represent the actual case. You will also obtain corresponding theoretical or experimental results to compare it with your simulation. So you can try to, if you want to, try to imagine what can be also the possible results I have, to know what is the physical and the physical situation you are in. So you can do some research to know what are the results I can expect. And as I told you also, you might do some simplifications if they do not affect your result. So these steps are important, especially to obtain the correct boundary condition. So also you should specify what are the boundaries of your problems, because these are the inputs that if you don't implement accurately, you will get bad results. So you should search for your boundaries or measure them. Sometimes you measure them experimentally and you prepare them to be used in the setup process. So for example, if you want to simulate airflow over the wing of a commercial airplane, you have to know the range of speed for that wing. And you will also look for previous experimental or numerical results done in the field. Now, concerning the other steps, as we said, in the geometry, we'll have to make the geometry. You can use ANSYS, or as we said, you can use any other software and import your geometry. For example, with ANSYS, you can use AutoCAD, you can use SolidWorks, you can use Inventor, etc. In the meshing process, which is one of the most important steps, you will divide your space into small control volumes, and we will learn what is a good quality of mesh and what is a bad quality. Because if you don't have a good mesh, you might have divergence of results. So, so in general, if you have divergence in your results, the first thing you try to do is to enhance your mesh quality. You increase the number of elements, you do some strategies, as we will see together, which are phase sizing and inflation, to enhance its quality. Now, concerning the physical setup, it's done in the solver ANSYS. The physical setup will give inputs for solution accuracy, boundary condition, physics involved, material involved, the properties involved. So here you will implement all conditions of your system, and of course you will select the numerical algorithms that will be used for your simulation. And finally, to start ANSYS, this is what you should do. You go to ANSYS Workbench, you select Fluid